What is general theory of relativity? If I go by the definition, it was discovered by Albert Einstein and published in 1915. It is considered a geometric theory of gravity, where gravity is not considered as a pulling force but something which bends space and time by mass and energy. It also generalizes special relativity and refines the good old Newtonian mechanics. Well, this kind of a theory has got some peculiarities. First of all, the basic concept of force as something pulling and falling turns in something which is called a space-time curvature. So as you can see that the apple dropping on Newton's head now is considered as a curvature which creates a dent on a fabric, and you can see particles and bodies moving around. Straight lines, the basic Euclidean distance, now turns in geodesics. So this is also considered a new change in terms of understanding physics. Space and time, which was considered as two distinct and independent identities, are now being united in what is called a space-time continuum. So Einstein's general relativity completely transformed our view of gravity. Instead of pulling force, gravity is now considered as the bending of space and time themselves. Well, prior to Einstein, space was thought to be a stage, and here all the particles and the entire phenomena of universe is going around, and time actually flowed uniformly everywhere. But in general theory of relativity, as you can see this animation shows, space and time are interwoven into a single identity which is called a space-time. Also, in classical mechanics, mass actually had two roles. First, it was inertia, resistance to change in motion. In Newton's second law, you can call, which is noted with this equation, and mass was also considered as a source of gravity, the gravitational mass that creates and fills the gravitational force. Now what had happened is these two masses, inertial and gravitational, were experimentally equal, but Newton treated as a coincidence with no Dicke explanation. So these two masses were experimentally equal, space and time were fixed, mass did not affect, and it only affected through force. Now in general theory of relativity, prior to that, when we come to special relativity, we found that mass is no longer just a weight. So if you go back to this particular area, you see the Newton's second law of motion and Newton's law of gravity considers mass and inertia to be something different. When we come with special relativity, we find that mass is no longer just a weight or resistance. Mass is a part of a big picture, that is, which is called energy. And this actually causes the entire thing to change, because now it includes rest mass, kinetic energy, pressure, stress, everything, radiation energy, and this is actually causing a dent in the space-time. That is what it is causing, the curvature. So all of this influence space-time curvature, and gravity is sourced not just by mass but by all forms of energy, which I have just stated as rest mass, energy, kinetic energy, pressure, and everything. So in general theory of relativity, a flat space object moves along a straight line in Newtonian mechanics, but in case of a general relativity we get a globe, and if we put up a particle around here, we will see that although the particle moves in a straight line from this point to this point, you will see that the red dot is actually traversing in a straight line, but it is coming to be curved because of the curvature of space-time. So that is a big issue. It is not considered to be something which is bent. It is traveling in a straight line, but the curvature is actually making things happen. So it is traveling in the straightest possible path, but the curved shape of the geometry creates something different. So the planets also are orbiting because they are pulled, but because they have a space-time curvature. So planets in general relativity are going around not because they are pulled, but because there is a space-time curvature. So all in all, at the first phase of the video, what I can tell you that this is what is called general relativity in a nutshell. Now when we're talking of general relativity, the question comes that why it is called general. Is that something very generic or something special prior to that? Well, let us explore in this part of the video. The left hand side you will see an image of a boy with balls floating in a train. So the train is moving with constant velocity, not accelerating most importantly. Inside the train the boy throws the ball and they follow the same physics. As you can see the parabola on the blackboard, and to him it looks exactly the same. And this was the principle of special relativity, that the laws of physics are the same in all inertial frames of reference. Now take this picture on the right hand side. Here you can see that the train is now accelerating, speeding up, slowing down or curving. Things do not behave the same way anymore. Balls roll on the table. The boy feels forces pushing him backwards or sideways. So special relativity cannot handle this situation because it works only for non-accelerating or inertial frames of reference. So when we talk of the term general, we want to say this, that when this inertial frame of reference means that it means that the laws of physics including relativity hold universally true in all possible cases. By all possible cases, we mean to say when accelerating frames, that means where velocity changes with time. For example, this person who is bicycling with a certain speed. Second, it also comes for this when it is a rotating frame. For example, frames that spin relative to others. For example, a rotating space station with artificial gravity. And also it happens with the gravitational frame. For example, a frame sitting in gravitational field of any strength. So when we say general, what we're trying to mean is that the laws of physics, including relativity, are basically covariant. That means they have the same mathematical form either if you're floating freely in deep space, or you're falling inside a black hole, or you are riding a roller coaster, all where these things will always be the same. So it is called general because, as I told right at the beginning, that general theory of relativity refines and redefines Newtonian mechanics, and it is an extension of special relativity where things were special. Why? Because they were inertial frame of reference. Now it is general. Why? Because it is a non-inertial frame of reference, and whether you're floating, falling or riding a roller coaster, the laws of physics will always be the same. Having said that, we come to the next part of our video, which is even more interesting, is that how general theory of relativity was actually discovered. Here's quite a quick whirlpool tour in understanding how general relativity was discovered. Now, after proposing special theory of relativity in inertial frame of reference, Einstein began to think of gravity, how it could be included in a relativistic frame. And during that time, he called it the happiest thought of his life, which he received. Now, I am going to demonstrate this happiest thought of life. But before that, requesting all of you to read the left-hand side part, that gravitational fields only have a relative existence because for an observer freely falling from the roof of a house, at least in his immediate surroundings, there is no gravitational field. Now let me quickly explain to you with a nice figure. Here you can see in this figure on the left hand side there is a black arrow. This shows a girl stands on the floor on Earth's gravity. She feels a downward force. That force, her weight pressing her feet against the floor. Now on the right hand side, now you can see this arrow which is showing that imagine a spaceship or the ship accelerates upwards with an acceleration g. So the girl is pushed against the floor just as if gravity were pulling her down on the earth. So she feels something, a pressure on her feet. Next comes this part. Now suppose the box is dropped in Earth's gravity. Both the box and the girl inside accelerate downward with the same g. And lastly, as you can see, if you consider this to be a spaceship drifting with constant velocity, no acceleration, no gravity, the girl feels weightless. And this is physically free, same to what is called a free fall. So from here what we can understand that there is absolutely no way to distinguish inertial mass from gravitational mass. So the girl would experience weight is essential just like being in free fall, except that the is pushing upward, backward against you. That is considered to be the happiest thought in Einstein's life, and this is actually known as the principle of equivalence, which came into play around 1907. Now, even prior to that, after getting these thoughts, when Einstein was trying to find out a theory of relativity, a very important personality comes in history of physics, special relativity, Marcel Grossmann, a Swiss mathematician mostly known for his works on differential geometry. He collaborated with Marcel Grossmann to find out something which is called the Entwurf document. In German, it means an outline. So the Entwurf document actually carried the seeds of general relativity, because Einstein was not aware about tensor calculus, Riemannian geometry, and with his friend Marcel Grossmann, they finally laid the groundwork of a covariant theory of gravity. History also tells that there was a kind of a debate who published earlier, David Hilbert or Albert Einstein, but we are not going to enter into any kind of a debate. What it tells that Albert Einstein presented the final form of the field equations to the Prussian Academy of Sciences shortly after David Hilbert submitted a similar formulation. So now what you are looking at the screen is basically the first page of the famous historical document, Session of the Physical Mathematical Class, and it was published in 25th of November 1915, The Field Equations of Gravitation by Albert Einstein, and finally on the 25th of November, General Theory of Relativity was born, and this actually marked the birth of what is called General Theory of Relativity. Now, as you can understand right from the beginning of the video, you are learning and I was talking about force. The entire idea and the concept of force has changed in terms of general relativity and that of Newtonian mechanics. So we will try to understand what is the core idea of force that actually changed. Now, if you consider Newtonian mechanics, force is basically the fundamental cause of motion. So as you can see, this person is pushing a book, it accelerates because of the applied force. So here we know we write F equals to ma, where F is the force, mass, m is the mass, and a is the acceleration. So as you can see, if you push a box, it accelerates because of the applied force. Similarly, gravity in another view is just also considered to be another force, and the famous law of gravitation by Isaac Newton comes across. So here also gravity pulls objects just like a rope pulls or a push or the box, the man pushing up the box. Now this picture was all okay, but Newton's picture really had a problem. And the problem was that it actually treated gravity as some kind of a mysterious force, or we can call it as action at a distance force. And the question arises that if the earth is going around the sun, how does the sun reach out to pull earth instantly? So how does the earth, sun reach out to pull the earth instantly, even if it is 150 million kilometers away? How does it do? So special relativity actually had nothing to do with gravity, and it marked that nothing can move faster than the light. So gravity as an instantaneous force actually did not fix in special theory of relativity. Instead of thinking gravity as a force, we consider this to be a property of space-time. Now here you can see there is a trampoline and the ball is falling right on the trampoline, and this is causing the curvature. So as has been told famously that space-time tells matter how to move and matter tells space-time how to curve. So the marble curves around the dip, as you can see on the animation, not because of an invisible force as perceived by Isaac Newton, like a hand is pulling, but because of the surface itself is curved. So likewise, Earth's orbit around the sun is not because the sun pulls it, but because space-time around the sun is curved. And we will see a proof on that in a few minutes time for that. So what we can understand how the fundamental idea of force changed, that it is the mass, the ball, which is causing the curvature. So mathematically, instead of force, Einstein said mass and energy cause the space-time to curve. So as here you can see this nice animation shows that objects moves around naturally in space-time, but space-time itself is curved near masses. So what happens is that what looks like force is really just a motion along curvature. So the famous equation of Newton's F equals to ma now becomes a little bit complicated, but don't worry, we will decipher this, and this is called a geodesic equation. More or less it is the same like F equals to ma. Under law of movement of force and gravity, we will reach back to F equals to ma. So Newton's answer was, in empty space things move in a straight line at a constant speed unless there is a force acting on it. But Einstein told that in space-time, which may be caused due to mass, energy, straight lines are replaced by geodesics. So let us understand one thing, that fundamentally at the deepest level both Newton and Einstein were asking the same thing. What is the most natural way things move when nothing is pushing them? So here for Newton it is moving in a straight line. For Einstein it is also moving in a straight line, but is replaced by geodesics, and the curvature seems that the light or the straight line is moving in a different path, but that is actually not. Essentially both of them are the same. So if I now see that Newton's law F equals to ma is basically telling what F force is acting on a body, m is the inertial mass and a is the acceleration. The question comes, what is acceleration mathematically? And we all know that acceleration is nothing but it is the second derivative of position with respect to time, and in calculus we write like this. Now if we substitute the value of a in terms of F equals to ma, we get something like this. So Newton's view, force is the cause and the curvature, the trajectory, is basically the effect. This is Newton's view. Now when we come to Einstein's view, he removed the idea of force and it called by the curvature of the space-time. So F equals to ma, as you have seen that it get replaced by little kind of this kind of a complicated equation, but it is not complicated, I can assure you. X mu is basically what is called the space-time coordinates. That means t will be the time and x, y, z as the spatial and the temporal components. The tau is basically the proper time, that means the natural clock of the particle which is following. And this gamma, which has got a mu and a alpha beta, these are called Christoffel symbols. Well, I'm not going to extol Christoffel symbols right now because it is going to take a time. You can understand for the time being that it is a connection coefficient that encodes the curvature of space-time. So what is important is that here also you can see a second derivative. Acceleration arises because of force. Here also you can see a second derivative. Acceleration arises because of the curvature of space-time, which is represented by Christoffel symbols. So here you can see there is a d square x mu. Here also you see there is a d square x, not the mu part. We're just adding because of the four coordinates of space-time. Here you can see again a second derivative, d tau squared, and Newtonian mechanics here also you see that dt square. So mathematically we can go back from F equals to ma, or rather I would say from the geodesic equation we can go back to F equals to ma, because essentially they are speaking the same. So here we come, you feel a force pulling you down, you are simply following a geodesic, that is a straightest possible path in curved space-time. So this is the core idea of force, which actually changed, which got a lot of modifications from a force to a curvature of space-time. Now all of this actually are coming from one central equation, perhaps the most beautiful yet a very difficult equation to understand, which is called Einstein's Field Equations. And we are going to quickly look in what is the basic understanding and meaning of Einstein's Field Equation. So as you already know, this is the core, the foundation, the pivotal force on which the entire edifice of General Theory of Relativity is built. Now, if you look at the textbooks, blogs, videos, you might find Einstein Field Equations in different form. This is the standard form, this is the original vacuum form, this is the geometric, this is the trace river form, this is the compact form. But essentially, it all means the same. The left-hand side of the equation measures the curvature of space-time, and the right hand side tells about matter energy content. So as put up by famous A. Wheeler, that space-time tells matter how to move and matter tells space-time how to curve. So essentially what we get is that it tells how matter and energy in the universe determine the curvature of space-time, and all these tensor equations and complicated mathematics actually measures that. If you see, there is a mu nu component in the Einstein field equations, and it is basically talking of one temporal direction t and three spatial directions x, y, z. This animation is a kind of an abstract idea how it would look like for a four-dimension space-time. So this mu nu is basically all the four dimensions. This mu again a fourth dimension, again and again. So we get total 4 plus 4 plus 4 plus 4, 16 kind of a differential equations, which can be reduced in 10 ordinary different 10 partial differential equations. We don't have to deal with 16. Now here you can see in Einstein field equation certain terms you already know. What you know first of all is a lambda, which is called a cosmological constant. You also know what is c, that is called the speed of light. You know what is 8 pi, which is a constant. You know the good old g, which is called the Newton's gravitational constant. But these constants are important. Why? Because they set the limit or the strength. That means certain values and we cannot go beyond those values. So g, for example, means that larger g would mean a stronger gravity and so on. C raised to the power 4, it ensures both sides have the equation of the same units. 8 pi g also gives you a curvature for the given amount. So don't ignore the constants. Constants are important. Why? Because they set a limit up to which level the energy, curvature or the mathematics will go about. Now let us come to those things which we don't know. The first is the R, and this is basically called the Ricci curvature tensor. You can just imagine it to be a kind of a ball which you are rolling around. So if you release two balls side by side in a flat surface, it would move parallel. If the geodesics are converging, they would meet, and if r is less than 0, that means they are diverging. So at one position it is 0, greater than 0 and less than 0. So this is how overall it means. Now we come to the second R. Now have you noticed this R has got a mu nu? That means it's a tensor component, it has got indices. This R has got no indices. That means what? It is a scalar curvature. What do I mean by scalar? It means that overall it is an average of the total kind of a curve without any directional preference. Because there is no direction, we don't have any indices, and that is why we call it a scalar curvature. What about this small g? No, it is not the gravitational acceleration g. It is called the metric tensor. Now, metric tensor is something which actually measures how distance, times and angles they actually do in terms of a curved space-time. So the metric tensor is simply a mathematical tool, and it tells you how to measure lengths, angles, volumes. So it is a kind of, you can think of a Google map algorithm that decides the real distances between two pins, considering curves, hills and roads, not just a straight line. Then we come to the cosmological constant, which we have already talked about you. And the next one, which is called the stress energy momentum tensor. This entire component is responsible to measure how much energy, how much momentum, how much density, how much flux, all these are causing the mass and which is causing the curvature. So the real reason of the curvature is on the right hand side, and how the curvature is measured is on the left hand side. If you really want to go a little bit more deep in understanding, I've got a video which is called What is Einstein Field Equation, and thanks to all the subscribers and the viewers, this video has done really well, and you have all watched it like other videos. You can go and find it in the playlist of VSC, What is Einstein Field Equation. Now, as you understand, every scientific theory, no matter how beautiful or elegant it is, they ultimately face what is called a test, the reality. Now, Einstein's general relativity is not an exception, and its real power is seen in how its bold predictions have stood up to some of the toughest tests in the world of physics. And in this part, we will look at what are the proofs of general theory of relativity. Now, a proof in mathematics generally is called where we establish certain things using logic and axioms and they become absolutely certain, isn't it? But it is not for physics. For physics, we use mathematics as a language, but they are not abstract structures. Physical theory makes prediction, and these predictions are then tested against experiments. And for general theory of relativity, the first test came, which is called the perihelion precession of Mercury. Now, the word precision actually comes from the Latin word pre, which means before, and ceder, which means to go. So in physics, generally we refer to the slow and gradual change in the orientation of a rotating object. As you can see here, this is a spinning and its axis does not stay perfectly upright. So it keeps on wobbling here and there, and that wobbling motion is called a precession. So there are two types of precession. If it is a spinning object, it is called an axis precession, and if it is an orbiting object, it is called an orbital precession. So let us be very careful about these two words, because there is a precision in English which means how close repeated measurements are to each other, regardless of whether they are correct or not. And precision, which has got a double S, actually means rotational motion in astronomy. That means precision is the change in the orientation of the axis of a spinning object. Now, we astronomers have already observed what is called the perihelion precession of the Mercury, and this nice animation actually shows this. So Mercury goes around the sun in an ellipse, which is an oval. The closest point of the Mercury's orbit is called a perihelion. There's something which is called a aphelion. If you know that what is, you can put it up in the comment box. And over time, the astronomers have found that it actually shifts. It shifts forwards in space, meaning Mercury's elliptical orbit slowly rotates around the sun. So this slow rotation was actually what is called a perihelion precession. But there was a problem. So astronomers knew this since 19th century. But there was a problem, and there was a mismatch. The mismatch was this, that observed precision was around 575 arc seconds per century, as explained by Newton, but the unexplained remainder 575 and 532 was 43 arc seconds. And this, believe me, was a big headache for scientists, because Newton's law had explained everything else so well. So why there was an unexplained remainder? What was the problem? And that is where actually general theory of relativity and Einstein's genius actually come across. So what Einstein's general relativity told is that the sun's mass actually curves space-time. So remember, Mercury actually being very close and moving very fast actually feels this curvature more strongly than any other planet. So what happens is that this curvature, its elliptical orbit to rotate, and the perihelion slowly advances. So the sun's mass curves space-time. Mercury being very close can feel it. This curvature causes its elliptical orbit to rotate, and the perihelion advances, and this amount actually matches with the observation perfectly. So here you can see the precise calculation of Einstein predicts an additional 43 arc seconds per century perihelion precession for Mercury, and this actually happens because of the geometry of the space-time. Because Mercury is so closely related and located to sun, it can actually curve and feel the curvature because of the heavy mass of the sun. So here you can see I have just given a quick idea that general relativity correctly describes gravity. It can explain phenomena of Newtonian physics which cannot, and this was the first observational triumph in general relativity, showing that Einstein's theory was more than a mathematical idea. This was actually the first page of Einstein-Besso manuscript, and this is how the speed up of the Mercury is shown. And this is the famous picture of Einstein and his his childhood friend Michel Besso. Actually, Einstein worked with his Michel Besso in solving this Mercury's perihelion precession. So they managed to calculate part of the perihelion precession, but did not get the full observed idea, and Einstein later called it as Besso calculation, and even acknowledged in his letter that without Besso he might not have got there as quickly as he did. And this, you will be thrilled to see, this is actually the page where Einstein have calculated Mercury's perihelion precession. Few things are quite noteworthy. Number one, this is written in German, Jahren. I'm sure I'm making a wrong pronunciation. This is called precession in 100 years. Now, why it is 100 years? That the relativistic correction Einstein was calculating was extremely small per orbit. So if you measure just one orbit, the shift is impossible to detect. So astronomers usually report orbital precession as an accumulated effect of 100 or 200 years. Say for example 100 years here is a century. So that way the number is large enough and it is easy to compare with observation. These little signs of Einstein's handwriting talks of arc seconds. This is arc minutes, and here in German what it is written is called independently verified. Now what do we mean by that? Now the phrase independently verified actually means that Einstein's prediction of Mercury's perihelion precession 43 arc seconds per century was checked by other scientists also and matched with astronomical observation that had already been recorded. So this is why this independent confirmation was one of the first strong proofs of Einstein's general theory of relativity. So this is the page of Einstein I have just given. You can pause the video and read it. So first was 31.5, then was 30 arc minutes. The difference was 77 per century. Out of this, Newtonian gravity explained most but cannot. And then Einstein general theory of relativity finally explained this anomaly. So it actually showed that space-time curvature predicted by general relativity is real. The perihelion precession of Mercury provided the Newtonian gravity was complete, and that space-time curvature as predicted by the mathematics now gives the missing piece, and now we actually can see the actual calculation and a big triumph for general relativity. The second and perhaps the most famous test of general theory of relativity was not done by Einstein but by a British astronomer and mathematician, Arthur Eddington. Eddington actually measured certain things which carried quite an important thing. So Einstein prediction was later tested by Eddington. So Eddington led experiments and expeditions on the 29th of May. There were two teams which went, one to Africa, Principe Island, another to Sobral in Brazil, and they photographed the stars that appeared close during this eclipse. Now why there was an eclipse? Because that is where when the curvature of space-time will be more and more predominant. So here you can see during the eclipse the light was straight, and during normal position, and during the eclipse it actually bent. So you can see again Einstein predicted 1.75 arc seconds, Newton was 0.87, Eddington's data was matching with Einstein, and this was a very big proof, the first direct evidence that mass curves space-time and light actually follows curved path, and this was a big triumph on Einstein's general theory of relativity. Here you can see this nice animation actually shows it, that here is a mass, the sun, and light is actually causing the curvature and reaching our eyes. So it seems that the star is located somewhere else, which is actually not. It is actually the light which is traversing in a different direction and reaching our eyes. This is a big triumph, and New York Times actually celebrated by publishing this one. Lights all askew in the heavens. This is a cutting of the 1919 New York Times, which was published on November 10th. And this actually is the exact match in terms of Einstein's prediction. Apart from that, if I go chronologically, there were other proofs of general relativity also. First one was gravitational redshift around 1907, where light loses energy as it climbs up to a gravitational field. The next was gravitational time dilation. Time runs slower in stronger gravity and compared to weaker gravity. Then came the gravitational lensing around 1919, which I just showed you. Massive objects bend space like light like a lens and distorting the view of the distant galaxies. And finally, very recently in 2015, we got the triumph, which is the gravitational waves. That means ripples in space-time caused by accelerating massive bodies like merging black holes. So on a one-line summary, we can say light shifts red in gravity, clocks take slower in gravity, and mass bends light like a lens, lensing and massive body send ripples through space-time, which are called gravitational waves. However, Einstein's general relativity completely reshaped our view of the universe, but it is also had got certain consequences. These are not science or science fiction ideas. These are really measured and these are called what are called the consequences of the general relativity. Let us explore in this part of our video. Now, when we talk of the consequences of general relativity, I am trying to mean this. What actually happens when you start solving Einstein's field equations? Now, hold on. I'm going to give you a simple analogy so that you can understand. Now, think of Newton's second law of motion, F equals to ma. And if I tell you that there is no force, F equals to 0, then solving it will give you an equation something like this, which will give you an equation for this. So what does this mean actually? It means that the body moves in a straight line with a constant speed, if I consider F is equals to 0. So this is how solving an equation yields to a solution. Now let us consider Einstein's general theory of relativity, and as I have already explained, the right hand side T, the stress energy momentum tensor, holds entirely or houses everything related to mass. Now suppose we do not consider any mass, T mu nu is equal to 0. So the solution, if you put the value of T mu nu equals to 0, we get what? We get something which is called a flat space or a Minkowski space, and the metric something looks like this. And don't worry if you don't understand this metric, it means actually flat space time. Now similarly in Einstein's field equation, if instead of doing this, if I say that there is a spherical mass something like this, which is sitting in space like a star, and still nothing else, solving the Einstein field equations actually gives what is called this one, the Schwarzschild metric. And before understanding Schwarzschild metric, we need to understand what is called a Schwarzschild radius. Let us look up quickly. So till now what you have understood, that solving an equation given certain values yields another solution. Here we are not considering any mass. To make things simple, we are considering a spherical mass which is not rotating, which has got no charge, and solving this gives a Schwarzschild metric. But let us understand what is Schwarzschild radius. This was done by a brilliant, astounding mathematician Karl Schwarzschild, a German mathematician and astronomer, and he founded this equation when he was actually serving for First World War, and there were no computer, nothing, no calculator even, and he calculated that working under the bunkers of First World War. However, this is what is called the Schwarzschild radius. Schwarzschild radius is actually coming out from Einstein's field equation, and the conditions are that the mass is spherically symmetric and it is non-rotating. So if I consider a mass, for example, m is compressed, very much compressed into a small sphere. It is compressed into a sphere of radius smaller than Schwarzschild radius Rs, then even light cannot escape, and that is where the concept of black hole emerges. Let us consider a mass m. Let us compress it even lower than the Schwarzschild radius. We get a zone where light cannot escape. So for example, Earth's Schwarzschild radius is 9 millimeters. That means you need to compress our entire Mother Earth in an area which is just 9 millimeter. Similarly, Sun's radius, Schwarzschild radius is 3 kilometer, and so on. So remember, this Rs is not the physical size. This is basically what is called the critical radius, where escape velocity becomes equal to the speed of light. So this Schwarzschild metric is basically, you can consider this big equation. We are not going to look in that because that is not important. How space-time behave around a heavy spherical body which is spherically symmetric, and it should not be rotating. And if it rotates, it is not spherical metric, it becomes different metric. There are curve metric, etc., which I am not discussing right now. So here we write the Schwarzschild metric, and in order to make things a little bit simpler, I will reduce this part to this. So r squared d theta square plus r square, this I won't write, rather I would put it as d omega square. So it is the same thing. These coordinates are now compressed and put up in a shortcut like this. Now we will just look up in two different zones of the Schwarzschild metric. The first one is this one, as you can see here. What it is, you can see there is already something you know, dt squared. That means there is a time. You're right. So this actually tells how time ticks. Closer you go to the mass, this factor shrinks and time slows down. So as r approaches Schwarzschild radius, the time slows down infinitely, and that is what is called time dilation. Now let us zoom in this part. You already know what r is. What is r? R is radius. Exactly. So this part actually tells how radial distances stretch as you approach Schwarzschild radius. Again, a radius approaching a Schwarzschild radius, the denominator becomes 0. And the third part, which is this one, is nothing. This is just the geometry of the sphere. So at the Schwarzschild radius, the inside, the internal structure actually becomes 0. And things starts to take a very interesting part. And we will look up what it is. So we have seen that at the Schwarzschild radius, the inside becomes 0. So the term, if we substitute when r approaches rs, 1, and the lower, the denominator becomes 0. So the term is something which we call undefined. Remember, 1 upon 0, when we are talking that this is approaching. So r is approaching rs. So at slowly it will become 0. So it will become undefined. Now here is a catch. And the catch is very important, and it is very central in the understanding of a concept. Then why do physicists call it infinity? You have heard in black holes and Schwarzschild radius, people are calling it reaches infinity, the equations blow up. What it is? Let me explain you clearly. Now physicists actually don't stop what is called undefined. So what they do is that they take a limit as r approaches 2gm upon c squared, and the limit actually looks something like this. And this is very simple. So what it happens as r, at r, when it becomes equal to rs, this cancels out. 1 minus 1 equals to 0. And for r greater than rs, denominator is always positive. But remember that the denominator is very small. So denominator is 0 but positive and tiny, so the whole expression is positive. That means it is 0 plus. Now comes the main magic. Since the denominator becomes a tiny positive number, say for example 0.00001, the fraction becomes a positive number. Very importantly, denominator 0.01001, value becomes 1000. Again, denominator 0.001, value rises, and further. So r, as it gets closer to the Schwarzschild radius, the value grows without bound. And that is why we use, or physicists use, the term infinity, because it blows up to infinity. So r gets closer to the Schwarzschild radius, the values grow without bound, and that is why we call it as blow-ups infinity. So instead of saying undefined, the physicists describe this behavior as something which is positive infinity, and it diverges and it blows up. So yes, pure mathematically, when r is equal to rs, it is undefined. But physics looks it as the limit, infinity, so we call it blowing up, and things become, I would say, infinity. So remember that the metric coefficient, which we are talking about, the limit value, it goes to infinity, meaning distances in the radial direction stretch without bound as you slowly approach Schwarzschild radius. So this gives birth to black hole concept, a region of space-time where space-time is so curved. Remember, the denominator, it is so small that the horizon, or the event horizon, or the entire space-time is blowing up to infinity. It is becoming huge and huge and huge. So here you can see, this is a nice picture that from an outside observer view, time stops and space stretches out. Why? I have just shown you mathematically. And that is why, remember that black holes are not assumed. Right? They are just natural mathematical consequences solving Einstein's equation, given a Schwarzschild metric, given a spherically symmetric and a non-rotating mass. It actually leads to what are called black holes. So they are not mathematical consequences. Solving Einstein equations in a vacuum or a massive object actually yields to this. Now, among the other consequences of general theory of relativity, I will just give you a quick idea. Clocks run slower, which we have seen this. We have also seen that gravity traps inside everything, the basic concept of black holes. Also, the bending of light, which was the famous Eddington experiment. Lights followed curved space-time, making massive objects acts like a cosmic lens. And we have also discovered gravitational waves. We have also seen how Einstein calculated the perihelion precession of Mercury, and space itself stretches, carrying galaxies farther and further apart, as we have seen with the Hubble's telescope. So these are what are called the consequences of general relativity. Also remember that every great theory has its triumphs and also its boundaries. And general relativity has explained gravity with a breathtaking accuracy from the orbit of Mercury to black holes, gravitational waves, yet like every scientific theory, it is not the final word and it's got its limitations. In this part of the video, we will understand what are the limitations that general relativity has. The first we have already discovered, singularities, because general relativity predicts regions where space-time becomes infinite, like black holes or the Big Bang. These infinities signal that the theory actually breaks down. Then we find some kind of an incompatibility with quantum mechanics, because general relativity is a classical theory while the rest of the physics, particle forces are quantum. So no complete theory has yet been found which unites gravity with quantum mechanics. General relativity also describes beautifully things, but it is unable to describe what are called galaxy rotations, and 95% of the universe is dark matter plus dark energy, and it is still mysterious. Finally, we get attempts to quantize general relativity, that means treat gravity like other quantum fields, leading to unsolvable infinities. So we call it non-renormalizable theory. This makes general relativity mathematically incompatible with quantum theory. So as a whole, we can say that it breaks down at singularities where space-time curvature becomes infinity. This equation often leads to physical quantities blowing up to infinity, predict infinities. It is non-quantum in nature. Also, it is non-renormalizable. That when it attempts to quantize GR produces lot of infinities, and it has got a limited testing range because it has only been tested in certain conditions like solar eclipses, black holes, but leaving extreme regimes still undefined. So it is definitely powerful but incomplete, because it is like a brilliant half of the puzzle waiting for quantum gravity to fill in the rest. From here we move that in order to meet those limitations, currently, recently, what are the alternative theories which are coming? What are the theories that are trying to get out of those limitations and get a better theory? Now, in order to do that, first of all, we need to look in the 1950s and 60s, these two great mathematicians and physicists, Robert Dicke and Carl H. Brans. So what was happening, I will tell you, they were actually still testing GR and wanted to see if Mach's principle, the idea that local inertia depends on the large scale distribution of matter in the universe, could be incorporated or not. So the first important theory came from what is called Brans Dicke theory, or Jordan Brans Dicke theory, which was proposed in 1961. And here what happened is that instead of gravity being described as a curvature, these two brilliant physicists introduced something which is called a scalar field, and which is a phi. Now, what is the scalar field? What is this phi? I will come to that part. But GR does not fully satisfy Mach's principle. So Brans and Dicke developed what is called a scalar tensor theory of gravity. So what it did is very simple. The scalar field was introduced. Why? Because it was made to make gravity strength dynamic. Because Einstein's theory says gravitational constant to be same. Constant. So connecting local physics with the global matter distribution. I know this looks very intimidating, but don't worry, we are not going to look in this entire equation. But what we are going to find out now is that why Robert Dicke and Carl Brans actually introduced what is called a scalar field. Now there are a lot of advantages. First of all, why it is a scalar field? Because in Einstein general relativity, Newton's gravitational constant G is actually constant. This is something which is actually constant, which doesn't change. Now, Brans and Dicke thought something else. What if gravity strength is not really fixed? And indeed, with the curvature of space-time, it can vary from place to place or with time to time. So what actually happened is that this particular G is inversely proportional to 1 upon phi. This actually came in. So what they thought is that if we introduce a scalar field phi, it increases, gravity becomes weaker. If decreases, gravity becomes stronger. Because why? It is inversely proportional. So gravity, they thought, is not purely geometry. It is a scalar, and it is denoted by phi. and it will modulate, it will change the strength of the gravity as we move from place to place and time to time. So the geometry tells space-time how to curve, which we have learned, but phi tells actually how strong the curvature response is. So actually, as I am showing you that the idea came from Newton's gravitational law. So instead of putting it as fixed, they introduced some kind of a function. For example, g of t or g of x. So it will change with time g of t and it will change with space g of x. So Brans Dicke is famous because they're known to discover alternative theories where g is not truly constant. So that is the basic advantage of introducing a scalar field. So the scalar field actually is suited because coupling a scalar is much easier compared to that of a vector, because it has got a charge, direction, etc., which will make life a lot difficult. Here you can see the vector field as direction. So if g were a vector, then we have to find the strength of gravity, etc. A lot of problems. So a scalar field respects this symmetry and it becomes easier. Also, you will see that introducing a scalar field is the simplest way. Why? Because vector field would require again new degrees of freedom, etc. So overall, what we can say is that the scalar field acts like a kind of a cosmic bookkeeper. It keeps all the accounts, adjusting the local strength of gravity based on the overall matter distribution. So here you can see this intimidating big equation tells simple things. First is that gravity is not only shaped by space, but also by an extra field which is called the phi, and it decides how strong gravity is at different times. Instead of having a fixed gravitational constant, there is a scalar field which will take care of tuning gravity. So all in all, we can say Einstein's GR is geometry of space-time with one universal strength g, and Brans Dicke was gravity is equal to geometry plus a cosmic field that makes the strength of gravity flexible and connected to the mass content of the universe. I will give you a very simple analogy to make this Brans Dicke theory even more simpler. If you can imagine this scene that you are in a concert hall, and here you can see Einstein conducting the concert. The whole orchestra follows a single unchanging rhythm. The strength of gravity, you can consider the beat of the drum, is the same everywhere, like a drum playing at one fixed volume, guiding all the instruments. Here you can see Brans Dicke's theory says, what if the drum is not fixed? What if its volume changes depending on how many instruments they are playing? So Brans Dicke introduced a second invisible musician. That is what is called the scalar field. So this musician does not play a tune itself, but constantly keeps on adjusting the volume of the drum. If the orchestra is heavy with sounds, then the drum softens. If the orchestra thins out, then the drum glows louder. And here you can see I have given just a brief idea of all the alternative theories. I'm not going to talk one by one. String theory is there, where gravity and all forces come from vibrating strings. Loop quantum gravity, which tells that space-time is made of loops. Then there are various modified theories like Mond, FR, etc., and extra dimensions like Kaluza-Klein, etc. You can pause and read this. Overall, all these theories are attempt to go beyond Einstein and create a more complete picture of gravity that works with quantum mechanics and explains the missing puzzles of the universe. And from here, we come to the last part of our video, that we are still searching for what is called in search for quantum gravity. We have seen that general theory of relativity works very well with heavy mass and bigger objects. On the other hand, we have got Erwin Schrödinger and Paul Dirac, the fathers of quantum mechanics, dealing with microscopic objects. Can we get an equation? Can we get a theory which marries them to happily quantum gravity of unification, where the very big and the very small are all united in one single theory? So what does quantization actually, or quantizing gravity, means? So here you can see that this picture shows that quantizing means basically taking a classical theory. Here you can see this one coming so smoothly and reformulating it in with quantum principles. So general relativity is smooth, space-time is as a fabric, and here we get quantum physics, which is discrete, which has got probabilistic thing. And this is what is called quantizing gravity. So we are looking for, yet not found, a unifying framework which is called quantum gravity. Think that this is a classical light which obeys Maxwell's equation, and we are looking for a quantized light which follows the photons, or the quantum electrodynamics. So in physics, quantizing actually means we are taking the classical arena or the classical theory, the smooth manifold, the smooth fabric of space-time, and reformulating it so that it works with quantum principles. And in order to go for this quantum gravity, there are different approaches to quantize gravity. These are very modern, very recent. You have seen a lot of podcasts in my channel happening. And the first one is what is called the string theory. Here you can see fundamental objects are tiny vibrating strings. Gravity emerges naturally as one vibration mode, and it needs extra dimensions, which I told Kaluza-Klein theory, etc. The second one is called a loop quantum gravity. Space is not continuous but made of tiny loops of energy. And it gives space-time a quantum atomic structure, and it predicts a possible solution which is called the Big Bang singularity or a big bounce. By Ashtekar, a famous Indian mathematician, we have used Ashtekar variables, which is very much prevalent and applicable in loop quantum gravity. Then we have got a third one which is called asymptotic safety. It treats general relativity a quantum field theory, just like a quantum field theory, looking for a safe fixed point. That is why I have highlighted that point, which is a little bit glowing in the picture. Here actually infinities cancel out. It does not introduce any new dimension, but its purpose is make Einstein's general relativity consistent at very small scales. Then we have got what is called CDT, causal dynamical triangulations. The idea is to build space-time from tiny building blocks like Lego. It uses a sum over histories like Feynman path integral, and it predicts smooth space-time at large scales, big quantum foam at small scales. So these are the different approaches. So if I divide now the approach, you will see the basic is simple. First one, which is called a perturbative or a particle physics approach. Its goal is basically to treat gravity like electromagnetism, weak and strong. The method is to quantize gravity and find out what is called gravitons, the hypothetical particles. We have not yet been able to find out. And problems that arises are non-renormalizable. There are a lot of infinities. So string theory, etc. requires extra dimension, etc. So that is something which is called the particle physics or the perturbative approach. Then we come to something which is called a non-perturbative approach or a background independent approach. By background independent, I mean to say they try to describe space-time without assuming any fixed stage or background. Instead, space-time itself emerges and evolves out of the entire mathematics or theory. And examples are loop quantum gravity, causal dynamical triangulations, and so on. So this is the second, the non-perturbative approach. Another which is called an emergent gravity approach. Emergent gravity approach, here it tells that gravity is not fundamental. Again, it emerges like thermodynamics from microscopic degrees of freedom. And examples are entropic gravity, the famous ADS-CFT correspondence, or the holographic principle. So quantizing gravity actually trying to mean that making Einstein's smooth space-time obey quantum rules, turning continuous geometry into discrete probabilistic building blocks, just like photons are quantized as light. The attempts are going on, the search is going on, but we have not been able to find anything which can quantize gravity as of now. So that brings to the end of our video, and I will like to end this with this note that general relativity is not the final word, it is a chapter in our ongoing quest. Quantum mechanics and relativity are still in tension. It is waiting for another grand theory to be harmonized. The universe keeps secrets yet to be unveiled. And perhaps the deepest lesson of relativity is that truth is always bigger than our current equations. That's all for today's video. I hope you have liked this. Please put up your comments, and thank you for watching this video. If you have liked, please do not forget to subscribe to my channel and click on this bell icon so that you get all the notification from Physics for Students. You can follow me on my social media handles, which I'm quite active nowadays, not always with physics and mathematics, but something different. You can always contact me and write to my email ID, which I try to respond as early as possible. Thank you very much for this extended, although it was not a bit size, but a kind of a complete idea, whatever I can, about general theory of relativity. Physics for Students will continue surprising you with more such videos. We will soon meet you, but till then, may the good Lord be with you.